we will continue further in our lecture series, and many times in our control theory as well, we will need lot of numerical methods on the way, especially with respect to nonlinear systems theory, the things are not available in closed form. So, to go resort to that, and in linear systems also remember that we need some operating point first before we talk about a deviation dynamics, which we linearize and then interpret that as linear systems. We will talk about linearization in one of those lectures later. About the linearization method is useful, and then we will see some of these concepts, other concepts also like root finding and other things are useful in lot of applications actually. So, let us quickly review some of these numerical methods that are frequently kind of required in our analysis and synthesis actually. So, first concept that comes to mind is first problem is linear equation solution. Suppose you have Ax equal to b, and remember we know for sure that if A is some rectangular and things like that, A is a square matrix for which a determinant of A is not 0, that means A is non-singular and B is not equal to 0, then x equal to A inverse B, we know for sure. Okay. But A inverse is adjoint of A divided by determinant of A, and that requires a lot of computation. We do not want to go to that definition all the time whenever that is required actually. Okay. Now, the question is, why do we require this kind of solution in our control theory, and one of that is you can see some of these motivation part of it. Suppose we want to find out something like a this is a typical equation x dot equal to x plus bu, okay, and let us say we divide this x into like control state and uncontrolled state, like xc is control state, xn is uncontrolled state, okay, and we divide it in such a way that it is like dimension of xc is equal to dimension of u, okay. So, if I just consider the upper portion of the equation, that means xc dot is equal to a1 x plus b1 u, okay. Then I tell, okay, this B1, remember dimension of xc is equal to dimension of u, that means B1 is a square matrix now, okay. Then I will probably try to find out what is my equilibrium condition, that means this xc dot is 0, right. If I take about the control state equilibrium and I want to interpret that as a forced equilibrium point, that means my control activity is not 0 for that. So, I want to maintain that particular equilibrium point, okay. And then what is my control required for that? It is also like what is called as trim control in aircraft actually. Like if your aircraft flies steady and level, okay, you really require some sort of a trim moment, because remember your CG and CP are not at the same point. That means there is a continuously there is a gravity related, this aerodynamic lift related moment which will act on the vehicle actually. Okay, if I just tell that in a little small diagram, okay, this is something like there, and your CG will be somewhere here and CP is somewhere there, okay. So, that means this particular thing will give us some sort of a moment about that actually, okay, there is a turning moment sort of thing. So, you want to cancel that by using something like a equivalent moment actually, okay. So, that means you really require some sort of a small elevator deflection actually, okay. So, those trim control is actually, trim condition is actually a forced equilibrium point in aircraft flying actually, and those of you cannot relate that, we will see that a little later, or that is very obvious also, it is not too much. You can see that this problem from other example problems as well, okay. So, what I am looking at? I am looking at some solution for something like xc dot equal to 0, that means the control state are operating under steady state actually. If I really want to find out what is my control necessary for that particular situation, then I can find a control action that way, because remember B1 is actually non-singular, okay, and square and non-singular. So, I can take that way. So, if I apply this control action, feedback control, then I will assure that this happens to be 0. So, that my aircraft continues to fly at steady and level basically. That particular control is actually necessary for maintaining xc dot 0. If xc is h dot for example, and u is delta E elevator deflection, then this elevator deflection I have to compute it that way, okay. So, obviously, we require this type of solution. Now, this is A1 of x is nothing but our B, if I going back to that, that is our B, and this A is nothing but B1 actually in this case. So, we require this kind of solution, efficient ways of getting solution and things like that. Remember, this control has to be applied online also. That means, we cannot afford to have lot of computational time getting wasted for computing this V1 inverse. We do not want that actually. Okay. So, we want to have an efficient way of controlling, finding out this V1 inverse actually. So, coming back to that, so this is the equation that we are asking, and then we are observing that A inverse involves too many computations actually, and roughly the computational complexity sense, it requires n square into n factorial computations. Okay. So, that means, if A is larger and larger and larger, you are getting trapped in this computational complexity actually. So, you want to do it in an efficient way, and one of that efficient way happens to be like Gauss elimination, which we will see in this class actually. Now, this approach is not just suffers from this computational headache. It also suffers from these other problems, like what is one thing is called ill conditioning. Okay. Now, remember, A inverse is nothing but adjoint of A divided by determinant of A, right. A inverse is equal to adjoint of A, okay, divided by determinant of A. So, if determinant of A goes 0, okay, that means, if you have a singularity is approaching, okay, you are approaching singularity, then this is a serious problem actually, because you cannot just talk about division by that and things like that. Okay. And also remember, there will be like so many computations and lot of computation, all of these computations will have a small round of errors. And if there are too many computations, then round of errors can be large actually. Okay. So, you do not want to do too many computation in any situation basically. The computers are always like finite length you can take, that number and all that, you will have finite digits only. So, there will be round of errors all the time actually. Okay. So, given a choice, you do not want to do too many computation actually. Now, Gaussian elimination is a substitute to that, and instead of general things, we will just take it as a small example and try to see what is going on here. So, we have this kind of an equation, let us say 3 by 3, okay, and then all these, okay, this is, I think there is a small mistake again, all these are small x1, okay, this is small x2, this is small x3, these are all elements actually. Okay. Anyway, so this equation, okay, what we want to do? We want to reduce this equation, whatever equation you have in this A matrix, to be a upper triangular matrix actually. Okay. And we take advantage of the fact that if we multiply any row with by any constant and then take addition and add and subtract to other row, then the equation are not changed actually, equation remains same. So, then we will take advantage of that thing and then tell, okay, we want to reduce this matrix to a upper triangular form actually, okay, by taking advantage of this row transform, row properties actually, like row multiplication, addition, things like that actually. So, what do you do actually? Okay. So, we will try to see these elements, whatever you see here, okay, 1, 1, 0, this has to be all zeros actually. Now, 1, 0 is already there. So, I want to make sure that this 0 also happens here, okay, or this 0 happens here, either way. Okay. So, now I see, okay, how can I do? Like I multiply this particular thing by minus half, 1 half, and then add it up actually. So, that means I want to make sure that this becomes 0 actually. Okay. If I do that, then 2 by 2 is 1, then 1 minus 1 is 0 basically. So, that will pop up there, and corresponding to that, like say 2 minus 1 half actually. Okay, 2 minus 1 half is 3 by 2, like that actually, and 0 will not change this. So, that is the equation that I will leave with actually. Again, 2 minus 1 half is 3 by 2 here. Okay. Now, you see that this is already 0, 0, but I have to make sure that is also 0. Okay. So, I will multiply this element, this row by 2 by 3 this time, and then subtract it actually. Okay. So, if I do that, then I will end up with something like this actually. Okay. Now, this is a upper triangular matrix. So, I start looking at the equation from down to top actually. Okay. So, then it turns out that, okay, minus 1/3 is nothing but minus 1/3 of x3 is equal to 3, and hence x3 is 9. Okay. Once I get x3 value, then I put that, but this particular is nowhere in, is a function of x3, because this particular, so remember this, okay, let us do that. This particular thing has given me x3 equal to 9. Okay. Now, if I go this equation rather, this second thing, then I get 3 by 2 x2, okay, plus 9, because x3 is 9, is equal to 3 by 2. Okay. So, I try to solve this, okay, and if I try to solve this, then x2 happens to be minus 5 actually. Now I go back to the first one equation now, first this equation now, okay, and tell, okay, this is 2x1 plus x2, okay, x2 is already minus 5, so this is minus 5 equal to 1, right. Okay. So this then 2x1 turns out to be 6 and x1 equal to 3, okay. That is why you get x1 equal to 3, okay, x1 equal to 3, x2 equal to minus 5 and x3 equal to 9, okay. That is easy now. So what are you doing here? You are somehow trying to eliminate these so called pivotal elements and then make it 0 0, and then once you get an upper triangular matrix sort of thing here, you try to look the equations from bottom to top, because then they try to solve these equations straightforward manner actually, okay. So that is a Gaussian elimination. And now Gauss elimination suddenly makes this n square into n factorial operations, this reduces to just this much operation actually. Remember this is actually something like a very high computational thing to a very low computational thing, okay. Remember nq is nothing but simply n, not n factorial here, and that will get multiplied with n square, which is a lot of computation really. Yeah. So obviously it leads to a far lesser computation, and then hence it is kind of preferred actually, especially in MATLAB command window, okay. If you some of you use that, then you have a choice of using inv function, inv into, okay, b, which is like x, or the same thing you can do that using this slash s, okay, a slash b, that will give you Gaussian elimination actually, okay. So instead of using the first one, I will suggest that you use this one actually, a slash b, okay. Alright, all is well here, but see some problems actually, okay. What first problem is this Gauss elimination method will also encounter problems, okay, if the pivotal element happens to be 0 actually, okay. I mean the one of the diagonal elements becomes, suppose this is 0 now, okay, sorry, I will took it there. Suppose if you do this exercise and this happens to be 0, now no matter how much you multiply and try to add and subtract, nothing will happen to this one actually, you will not be able to do that actually, okay. So in those situations, okay, one easy way to do that, okay, is just to exchange the rows actually, okay. Suppose if this one happens to be 0 here, then you take the entire equation, you put it a third equation, and this one is substituted as for second equation, you exchange the equations actually, then proceed further. That is the idea there actually, okay. So this Gaussian elimination is a very standard practice now, and lot of people make use of that. Again, in MATLAB window, MATLAB command and MATLAB environment, I suggest that you use this one, okay. Anyway, now going back to the next concept, what we saw there is algebraic equation solution for linear systems. That means we are talking about, this is a linear sort of equation actually, right. Ax equal to b, what you have is actually a linear equation, okay. Now what if we have a non-linear equation, okay. Remember numerical methods are more powerful for non-linear cases and all that actually, alright. Now let us see something like this, f of x equal to 0, okay, and you want to find out what is x equal to, okay. And again the similar motivation there, like I can partition these states, whatever x dot equal to f of x u, into two parts. I still maintain that condition, dimension of x is equal to dimension of u. Then in this case you will end up with like x dot equal to 0 if I want to address that question. Then I have this nonlinear equation now, okay, right. So fc of x0 u0 equal to 0, that is the condition that I want to find out, okay. No, that means no, can I find out some u0, okay, which will satisfy this equation. U0 can be a function of x0, I mean that's okay. That means if I know a particular number for x, that is x0, what is the particular number for u which will give me that? That is why these 0 0 notations are there actually, okay. So I will go back to this equation now, fc is of 0, okay, fc of u equal to 0, and try to find out what is u for that. That is the motivation why you want to address this, particular problem actually, okay. This is just one of the examples why you need that. You may need for many different cases also actually. Okay. Now we will start with the simple solution sort of idea. First we will see what is a scalar. By the way, this has many numerical methods available. Okay. One of that which is popularly known as bisection method. That means if you talk about a scalar expression here, for example, and you tell, okay, I have two guess values now. Okay. Then there is something called a bisection method. And there are very other ideas as well actually. So this is not what I am talking here is not an exhaustive review of methods available. Okay. So what I am really doing here is rather talking about what is called as Newton-Raphson method, which is very neat. It has its own beauty basically, and that is what is mostly used in practice. Okay. That is why I want to review this particular method of getting the solution actually. Okay. So what you really want to find out in this case, remember nonlinear equation solution will require some sort of iterative solution actually. Okay. That means at one go you will not be able to find out, but you may need some couple of iterations before you arrive at the final solution actually. So what is the idea here? Now let us say that we are having some xk value. Okay. Some value for xk is already available and k can be 0 also. That means you can start with some initial guess. Okay. Then if k is 1, 2, 3, 4, then you have already some iterated values available to you. Okay. Obviously that is not the solution. That is why you want to do iteration actually. That means f of xk is not really 0. Okay. However, you want to find out a delta xk such that if I make xk plus delta xk, then f of xk plus delta xk is equal to 0. That is what that means. If my delta xk is proper, then xk plus delta xk will be a root of this equation actually. That is the whole idea there. Now I will interpret this f of xk plus delta xk in Taylor series expansion and tell, okay, these are all higher order terms and all that. I will not be interested in that. I will just suppress that and I will just take the first order term up to first order term, and this is what my equation actually. Remember, this entire expression is 0 because that is supposed to be a root actually. That is what you want to find a delta xk such that f of the xk plus delta xk equal to 0 basically. Okay. Right. So that is your aim actually. That is how we want to find a delta xk. Okay. That means this is equal to 0 up to that actually. Okay. Up to this term. Okay. Then I can relate that, okay, delta xk, this particular term is 0, hence this del f by df by dx evaluated at xk times delta xk, this term, whatever term is there, is nothing but minus f of xk, and assuming that this is f dash of x, remember that, evaluated at xk. Okay. So assuming that that is non-zero, I can do that actually, right. Delta xk, okay, is nothing but this term. Okay. This whatever term you see here, that is nothing but delta xk actually. Okay. This particular term is nothing but delta xk. Okay. So if this is delta xk, then this is my what I really wanted is xk plus delta xk. That is my xk plus 1. Okay. So this is this particular term what you see here, okay, is xk plus 1. Okay. That is why you f of xk plus 1 is 0 basically, right. That is what you wanted. So this is why you will get xk plus 1 is xk plus delta xk, and delta xk is nothing but that actually. Okay. So xk plus 1 is equal to xk minus f of xk divided by f dash of xk. Okay. That's the algorithm, and you keep on doing that until you get some convergence. That means you don't get too much, much of improvement afterwards actually. That is up to that, you have to do that and stop. Now pictorially let us see what is going on here. Okay, you have some f of x. Okay, some f of x arbitrarily it is plotted something like that. F of x equal to 0, and assuming that that is the 0 axis, of course. Okay. It starts with 0 0 probably, and then obviously what you want this particular value, okay, this particular value, okay, this is your root actually. Okay, this is what you really want ultimately, but you don't know the value to start with actually, right. So you start with some sort of a guess value. Okay, so this is my guess value. I will start with some guess value, let us say, and then f of x is that much, that is f of x, then f dash of x is nothing but the slope actually evaluated at xi. So, that is the slope what is giving me actually, right. So, if I compute this delta xi sort of thing, and if you see this is actually a linear equation. Okay. So, what you are doing here, xi plus 1 is xi minus this term actually. Okay. And if you just carefully look at it, it is a kind of a, if you start with this equation, straight line equation, and try to find out the interpretation, the meaning of that. That means, all that it tells me that I have a guess value, I go to that particular point where it intersects this particular function, then evaluate the slope, and with that extension of the slope, I will cut this x axis, this x axis somewhere, and that is going to be my next iteration value. So, again I evaluate the function there, I again take the local derivative, extend that, and wherever it cuts, it is my xi plus 2. Again I go there, and then I will proceed further actually, like that, and ultimately I will converge there actually. Okay, so, that is the interpretation of that actually. Multivariable case, there is a similar extension you can do. Now, if you want this f of x equal to 0, you tell okay, I will do the same exercise, that means I will take multivariable Taylor series expansion, okay, and then I will tell okay, in higher order terms I will neglect, and I want to find out a delta xk in such a way that xk plus 1, this is my xk plus 1 anyway, okay, this is my xk plus 1, that is going to be a root, that means f of xk plus 1 is going to be 0 actually, right. So, this entire thing what I see here, I interpret that I will find delta xk in such a way that this is equal to 0. Okay. Now, if that happens, then I define this fellow as ak plus 1. Okay. I define this del f by del x evaluated at k is nothing but ak, something like that, and then the equation tells me that ak times delta xk is nothing but negative of this particular thing f of xk, and hence delta xk is nothing but ak inverse fk. And remember, whenever you see this kind of a thing, okay, you can use Gaussian elimination. You can use Gauss elimination actually to compute that in a faster way. Then you can update, okay, and then you get xk plus 1 is xk plus delta xk. Okay. So, very similar to what you have here, okay, instead of divided by f that 1 by like f dash of xk, because matrix theory you cannot talk that 1 over matrix, that is not defined. So, we will tell okay, it is negative of ak inverse multiplied by that is the only difference actually, otherwise it will continue, and all these have the backbone of all numerical method, most of them will always rely on Taylor series expansion, whether it is root finding, whether it is Euler integration, whether it is many things will all rely on Taylor series expansion actually. Okay. So, all these numerical methods derive the strength from Taylor series expansion really. Alright, so the algorithm is again same, you start with some guess value and then compute delta x like that, delta xk like that, and then proceed your algorithm like that actually. Okay. And remember, in MATLAB, those of you are using that, you will be using that for scalar thing, okay, you do not have to do all this yourself. If you want, you can do it, otherwise in MATLAB there is a function called f0. Okay. If you use this f0 function, it will try to find out a solution around the guess value that you have to give actually. Okay. This function will demand a function which is written, and then there is a guess value it will demand actually. So, it will find out a solution around this guess value actually. Similarly, you can write this multi-dimensional root, I think to my knowledge is not available directly, but from optimization toolbox something is available. Otherwise, you can write your own function as also actually. Okay. This is the thing that you need to write anyway. So, the Newton-Raphson method algorithm sense, you start with some guess value, either you talk that as x0 or x1, okay, whatever it is, and MATLAB will start with x1. The index 0 is not defined in MATLAB anyway. So, you start with some guess value x1 and then solve for delta xk, and then update your xk plus 1 is like this actually. Okay. And then you continue until convergence, and convergence typically it is given either in terms of relative error or in terms of absolute error. Given a choice, relative error is my first preference actually, I mean first recommendation, because your problem relates that tolerance value that you select, okay, whether here or there, it should not be problem dependent actually, okay, it should be fairly independent. If you talk about 1% error, is 1% error whether you have a nanoscience problem or you have a rocket science problem, either way actually. So, in other words, the units can be very different, but still the relative sense is still 1% only actually. So, that is where most of the time I will recommend relative error actually. Okay. And absolute errors are sometimes necessary, because suppose you have this particular x k plus 1, what you see here, okay, is 0, okay, then there is a problem of division. So, then tell, okay, I will continue with absolute error, because I already have a physical idea of what these values are. So, with that will help me in selecting a proper value for this absolute error actually. That will be always my second recommendation. First recommendation is this one actually. Now, let us see Newton-Raphson method. How do you find that? You can find a root of the following equation, let us say. Okay, then you start with some x0 value as 0.02. Okay, that you can start with that. Okay, and then you tell, okay, this is my x1. x1 is nothing but x0 minus this. Okay, and then x2 is that, and x3 is that. You can continue, and you can see that there is some improvement here. 0.08 to 0.5. The 3 is, I mean, 0.8 to 0.5, there is 0.03 sort of improvement here, and then suddenly it is 0.01 improvement, and you do 1 or 2 more iteration, it will converge actually. That is the method, that is the thing. Okay, so what is the beauty about this particular method? Why do you emphasize so much on this? Is primarily because of this property actually. What it tells is this particular method has something called quadratic convergence property. And that it means that actually, that means ek plus 1, whatever ek I get at every instant, okay, these are all iteration values, but correspondingly I can calculate an E1, and E1 is nothing but x1 minus x0 here, E2 is x2 minus x1, like that actually, E3 is x3 minus x2, like that. So, if I calculate that way, and then it will turn out that ek plus 1 is something like c times ek square actually, okay, and normally this ek, if it is relative error typically, these are all less than 1, right, EKs are typically less than 1, and then if it is less than 1, EK square is still further less than 1, I mean it is very small value, and EK plus 1 will be a function of, I mean it is proportional to EK square actually, EK plus 1 is proportional to EK square, that means it will converge very fast actually, okay, that is called convergence, quadratic convergence property actually. However, there are several problems here, and one of the problems is it really requires a good initial guess value in general, and that too if you give a wrong guess value, it will converge to a wrong value actually. Okay. There is a possibility of doing that. So, what are the problems of this method? First of all, we will see couple of issues here, and first thing is this particular fellow, I mean this Newton-Raphson method does not converge at inflection points actually in general. What is inflection point? Odd powers actually, if you have something like that. If you have x minus 1 whole cube for example, it goes through, remember it is a solution, x equal to 1. Okay. I mean, you are looking for the solution, but it will never converge actually at this point of time. It will, if you just do iteration starting from some guess value, you will see that this is some convergence issues actually. And it turns out that if it is point of inflection, something like that, if it cuts nicely and go, it is fine. Point of inflection, normally it has some convergence issues actually. It will go close to that, but around that it will not converge actually. Okay. Root jumping can also happen. For example, if you take a sin x, you know several solutions are there. Okay, whatever solutions are there. Now, suppose you start with this guess value somewhere. Okay. Then, I mean, you obviously what you intended to find out some solution here. Okay, you didn't intend to find somewhere else actually. But remember this, if you just take the local slope, it will push you somewhere here, again you take the local slope, it will push you somewhere here, again you take the local slope, it will push you somewhere here. And ultimately you will be able to locate 0, okay, sin x equal to 0, okay, that is also a solution, but that is not the right solution, okay, because you started with this guess value with the hope that you will find out the solution. Okay. And one of these issues can be avoided by taking this something like a what is called learning rate actually. For example, xk plus 1 is equal to xk minus f of xk divided by f dash of xk. That is what we discussed actually, right. Instead of doing that, you tell there is alpha I will multiply where alpha is a number which is less than 1. Okay. So, if I select a small value, obviously I will not jump here, I will not take this much step, I will take another small step in this direction. So, I will be going here. So, instead of going over there, this I will not go here, but I will go here rather, because I will not take this particular jump. Okay, the entire thing I will not take. Okay, but this alpha will give me this much only. Okay, many of these numerical algorithms will have this alpha term associated with that, including optimization routines and all. This is called learning rate actually. Okay, and we can probably select a particular appropriate value, okay, which will help us eliminating some of these problems actually. Okay, so first thing is it doesn't converge around inflection point, it is a root jumping problem. Third is there is oscillation problem. Okay, remember this particular f of x has no real roots really, because it doesn't touch the x axis, it just goes away from the 2 actually. Okay, there is no solution really, but you are blind to that and you still wanted a solution. I mean, if you start with some guess value, it will, I mean, if you start with some guess value, it will try to go there and then it will try to come some, I mean, this entire thing will go somewhere here actually. Okay, you started with, let us say, something like 1 here. Okay, I don't know, whatever this one. Okay, right, and then it will try to kind of oscillate actually. It will just keep on doing. Okay, one will lead to other will lead to there, and things like that actually. And obviously, that is a very clear example here, because in such situation you see that there is no root actually. So, you are just finding out, I mean, you are posing a wrong problem to the system actually. Anyway, it is also like a local minimum or maximum. There is another issue that, okay, even if it really touches the axis, let us say, okay, then there is a problem also actually. Okay, why? Because the derivative turns out to be 0 at some times. If you have this function, rather let us say touch this axis, I mean, this somewhere around 0, that means this plus 2 is not there. Okay. In that situation also, what will happen is, as you approach closer and closer and closer, you will approach to that solution anyway. But once you approach closer to that solution, the slope becomes 0 actually. So, that f dash of x, okay, this particular thing what you see here, okay, that will turn out to be 0, and hence you will jump it actually, like you will come very close and then go back. That is where again this alpha term will help. If you have alpha term, it will not force you to go there actually. So, sometimes these adaptive learning rates are also nice. You start with a high learning rate, after a couple of iterations you reduce this value to a smaller value like that actually. Okay, so that way your initially you will not march slow, you will march rather relatively fast, but towards convergence you will also not diverge actually. Okay. You will stay there actually, that means. Now again division by 0 is very apparent, because whenever there is a slope 0, okay, then there is a division by 0 problem, which will not be nice either actually. There is another problem, that if you are at the solution point is f dash of x is not 0, but it is unbounded, that means infinity. Then also there is a problem actually. It is very counterintuitive, but it is actually there is a problem. We can verify that with this example. Okay, square root of x, if you see that, then this f dash of x star, f dash of x, remember what is f dash of x? Okay, f dash of x is actually 1 by 2 square root of x, right. So, the solution turns out to be 0. So, this that around 0, it is actually infinity. Okay, so then there is a problem there actually. You can see that there are many. So, that means there are many issues there for Newton-Raphson method, but if none of these issues are actually there, or you find some solution like learning rate fixing and things like that, then it actually converges very fast. That is the beauty part of it actually. Okay. We will go to the next concept. Many times we need numerical differentiation. Numerical differentiation, we know this is the definition. We can either define it that way, forward difference way, that means limit delta x tends to 0, f of x plus delta x minus f of x divided by delta x, or in a backward difference sense, that means f of x minus f of x minus delta x divided by delta x. Okay. Or you can find it in a central difference way. You can take positive, you can evaluate the function little positive, then little negative, take the difference divided by 2 delta x rather. Okay. So, numerically if you want to really approximate that, okay, you have an x0 value. Okay. So, you evaluate the function around x0 either in a positive side or a negative side or both ways. Okay. Then it simply comes from definition actually. As long as you take delta x small values, if I eliminate this limit condition, that is all you are doing here, numerical approximation. In the limiting sense, delta x has to be very close to 0, but instead of that you will put a small finite value and still evaluate the derivative actually. That is called numerical approximation actually. So, forward difference is like that, backward difference is like that, and central difference is like that. And it turns out that if you use either forward difference or backward difference, the error is of order delta x, but if you use central difference, the error will be of this order delta x square actually. Okay, so, obviously central difference is better in accuracy sense point of view, but sometimes you will be required to use forward difference or backward difference. Like for example, if you start with grid point 1, then the numbers are available only at grid point 2, then grid point minus 1 it is not available, then you have to take forward difference anyway, like that actually. But wherever it is possible to take central difference, my suggestion is to kind of opt for that actually, because the error is lesser in that. Next concept is obviously numerical integration. This is all about numerical differentiation. And now numerical integration sense, suppose you have a curve like this, whatever curve is there, I want to evaluate this integral, that means area under the curve actually. Okay. And one popular way of doing that is using trapezoidal rule. Okay. One more way of doing that is also there. For example, if somebody wants to do that, they can evaluate this integral, this area and this area like that actually. Okay. And then this area like that. So, that means you can simply hold the values of the grid point and then try to find out, okay, you can whatever f1 value at point x1, you can just simply hold that and find out this I1 actually under that, forget this inaccuracy here, whatever happens here. And similarly, you can try to evaluate this entire area, even if you add some little more area actually. Okay. So, that is one way of doing that, but little better way of doing that is I have these these function values anyway available to me. These grid point values are also available to me. So, why don't I evaluate using this trapezoidal and this trapezoid formula actually, which is there. Instead of doing that, I am interpreting as something like okay, I will not do this, I will just take out and I will evaluate this area rather actually, whatever I1. Similarly, I will carry on with I2 and things like that actually. So, that happens to be better obviously, and that is doable. Okay. So, the formula sense, okay, I want to have this entire integration. So, what is I have to take summation of all these I1, I2 up to In minus 1 and In actually, all these areas, whatever stripes I get, little stripes I get, those stripes I have to integrate, I have to evaluate and then take summation of that actually. So, that is what I am doing here, and assuming a uniform grid, that means delta x remains same, you can probably do that actually. Okay, delta x, I1 is nothing but f0 plus f1, this is the trapezoidal formula for I1, and similarly for I2 that is the trapezoidal formula, and you carry on with all that. Then it interestingly turns out that if I take delta x by 2 common, then it is f0 by 2 in the beginning and fn by 2 at the end, and all other things are simply summations actually. Okay. So, right. So, if I take these two inside and then take delta x common here, then area and by trapezoidal rule is given like this actually. And also remember, there is a small comment out here that if you do numerical differentiation, it is always error amplifying, whereas numerical integration is always error smoothing actually, smoothing. Okay. Because see, if you do this numerical differentiation, these formulas, suppose you have a little error, let us say the function has not nicely this way, but the function has something like small error actually. That means the function is something like not this way, but something like this. Okay. So, now what will telling, if I evaluate a slope here, okay, I evaluate a okay, alright, I evaluate a slope here, it will be like this, and I evaluate the very next time it is like this actually. Okay. Remember, the values are quite different actually, one is almost like plus infinity, other is minus infinity. Okay. So, that way even the values of the functions are very small. The value at the slope at here, what I am evaluating, and value of the slope here are very different actually. That means, the differentiation operator is highly error amplifying. So, if you really have a noisy data or directly experimental data, things like that, never ever do numerical differentiation directly on those data. That's a strong recommendation rather. However, if you do numerical integration with respect to this and with respect to an average curve, let us say that is an average curve. Okay, so there will be some area which is getting added, some area which is getting subtracted. So, you do not have to really know what is the exact area value under those noisy data, but if you do the integration with it is rather okay. Instead, it will try to smooth out the errors actually. So, if you generate a raw data set using your experiment and things like that, to do either differentiation or integration, do not do numerical differentiation. Okay. You can probably fit a polynomial and then take differentiation on that polynomial. That is actually a recommendation instead of directly taking numerical derivatives like this actually. Okay. Alright, so these are numerical integration. Then the next concept that is needed for our kind of thing is actually ordinary differential equation solution. You know, remember many times you will do dx dot equal to f of xu and you want to integrate those equations and then find out what is the solution given a u basically. Okay. So, now some of these concepts before you do that, okay, the ordinary differential equations in general can be written in some equation like that. Okay, it is called ordinary because it has only one independent variable, namely time here. Okay, if you have more than that, you can talk about PDEs, partial differential equations actually. We will not be worried about those things here. We will worried about ordinary differential equation here. Okay, and there is something called concept called order and degree. Okay, order of the differential equation is the highest order derivative in f, and well, not really f actually. I think it is n x. Okay, highest derivative of x of t. Okay, so that is what you see here is the order of that, and the degree. Okay, degree is the exponent of the highest order derivative actually. Okay, that means if you have d square x by dt square to the power cube, okay, then it is the degree 3 basically. Okay, so this in general is a nonlinear equation. So, it can happen, the nonlinearity can come in higher order derivatives as well actually. So, you take the highest order derivative and then see what is the power of that actually, and most of our problem the highest order derivative will contain degree 1. Okay, so that way we will always work, most of the time we will work with degree 1 actually, but order can be arbitrary. That means you can talk about second order system, third order system, nth order system like that actually. Okay. So, for a small example you can see this kind of thing, the degree is 4, okay, because this first order is the highest order derivative which is 3, okay, and this particular term has degree, this exponent 4, so that is degree 4 actually. These are simple concept here. Okay. Alright, what is the solution of ODE then? A problem involving ODE is not completely specified by the equation alone actually. Okay, you have to talk about some boundary condition, namely the initial conditions, and typically you do not call that as initial condition because the condition can be given at any point of time. You can still integrate either forward or backward. So, it need not be only given at t0, it can be given at tf also, but it can be given any point of time really. You can integrate the equations both forward as well as backward using negative delta t, that is also okay. So, if you talk about an initial value problem especially, then the boundary conditions are given at initial time ti. Okay. Otherwise, okay, and if it is all the conditions are given at any point of time, okay, either including tf, that is still called as initial value problem only. Okay. Otherwise, it is something like split boundary conditions, like part of the boundary conditions given at one point of time and another part of the conditions given at some other point of time, and these problems are still possible to solve, but these are complex to solve. That means it will require something like some algorithms to solve 2-point boundary value problems, and optimal control theory will rely some of these things. In optimal control will invariably be required to solve 2-point boundary value problems actually. But this particular class will talk about initial value problems only. That means all the conditions are given at one point of time. Then how do you get that? Okay. So, numerical solution to initial value problems. This is the problem eventually. Okay. Dx by dt is t x of t0 is x0, and remember this can be in general. Okay. This x is actually a vector x. Okay. That means it is actually x1, x2, x3. Okay. All these components are there for you actually. Okay. So, this is not necessarily a scalar equation, this is a vector equation. All these n equations are there, x1 dot, x2 dot up to xn dot, with all initial conditions available. Okay. Then how do you get a solution? That means, what do you mean by a solution? I want to find out what is my, okay, I know x of t0, I know that. I want to find out x of t1, x of t2 and things like that, whatever time x of tn, I can still continue further. And remember, t1 is nothing but t0 plus delta t, okay, and t2 is equal to t1 plus delta t, like that actually. Okay. So, if I, alright, let us do that. Okay. Delta t, like that actually. And these delta t's need not be same, it can be different also. Delta t1, delta t2, like that you can also do that actually. Most of the time delta t is taken as same actually. So, the first approach, what is very simple rather, is called Euler integration in fact. Okay. So, what do we do here? Okay, quickly we will go through that. All the numerical integration methods will rely on what is called as tangent slope method actually. I mean, normally it will try to approximate the curve. So, remember x dot equal to f of tx. So, that means this is actually a function for which you can evaluate the slope at any point of that x0 value. Suppose you know x0, x1, whatever it is, and corresponding t's are known to you, then the function is completely known to you as a function of t and x actually. So, you can eventually take, I mean, you can take derivatives of that function and then take this the slope and slope of that line and things like that, yeah, and you have to exploit that. That means, using that equation of the line, slope of the line, things like that, you use that information to predict the next value of the solution actually. Okay, so that is what we will do. And very quickly see the Euler method. If you have dx by dt equal to f of tx, again this x is vector here. Okay. That means, with x of 0 equal to b, then at any start point of time, whatever point actually, suppose I know the solution for tn already, I want to find out for tn plus 1 actually. So, at t equal to tn, dx by dt, I can go back to my differentiation formula, okay, and use this forward difference method, I mean approximation, right, that is my dx by dt. So, I can use that xn plus 1 minus xn by delta t, that is forward difference, and this is nothing but f of tn xn. Okay. So, using forward difference formula I can do that, and then you simply solve this xn plus 1, okay, this x plus 1 will turn out to be like that. And remember, x dot, I mean fn plus 1, what you hear is nothing but xn dot actually. So, that means, if you xn plus 1 is equal to xn plus delta t into xn dot also, you can sometimes people write that way, with that thing that xn dot is nothing but f of tn xn. Okay. So, if I know a tn xn value, I can calculate this f of xn, I mean that is because this f is known to me, I can calculate that and then plug in this formula to get what is my xn plus 1 actually. This is very easy rather. Euler method is extremely easy compared to all of the methods, and we use that in systems theories many times, but then with the I mean conscious information that Euler integration is not very accurate actually. Okay. For getting good accuracy, you have to use delta t very small, because if you do Taylor series expansion, that is that tangent slope approach and things like that, in Taylor series expansion of this particular function f of tx, you are only retaining first order derivatives actually, all other terms you are throwing out, and because of that the accuracy is more and more better and better, provided delta t is very small actually. And if delta t is very small, you are going to take very baby steps, very small steps actually, which is typically not good in control theory either actually, because sometimes you may be caught with the trivial delta t. For example, delta t is 10 to the power minus 6 as 1 microsecond, and within that 1 microsecond control of the time is extremely small, and in my knowledge I have never seen a control update frequency of that small. Delta t being 1 microsecond, I have never seen. It's all like millisecond level I have seen actually. Okay. So you cannot do that if that problem demands that actually. The second issue is, suppose you want to do it in a faster way, tell the okay, you can argue that all other numerical method, we are going to see one more by the way, it will demand little more computation for every iteration. This is the smallest amount of computation by the way. So computational advantage I will have. However, suppose the other method gives me relatively larger delta t, okay, I can use that because accuracy will be high, and here the accuracy is being less, I have to use a lot of these grid points actually. So I have to repeat this computation so many times before I go from here to here, whereas in the other method I can go directly there actually. That means even if I am using a little more computation for every step, I have to work with less number of steps actually. Okay. So these are all I mean kind of advantage, drawbacks, things like that actually. Another advantage of Euler method is because the formula turns out to be rather easy. You can do further algebra rather easily. For example, if you discretize this equation this way, this is the discretized form of this continuous equation, then you can talk various derivatives of this. For example, you can talk about let us say del, okay, sometimes we are required to take derivatives actually, like del x n plus 1 divided by del x, okay, this is n plus 1, okay, divided by del x n. Suppose we want to take that, okay, then using this formula it is rather easy actually, because f n is this way, and you can take out all the derivatives I mean in a longhand formula basically, closed form formula, that will not be difficult. So there are advantages, drawbacks with this Euler method. My suggestion is just use it cautiously actually, don't jump into that. Some useful comments I have already told among those. Euler integration is this error is of order of delta t square, is not very highly accurate. So small step size is necessary, okay, and this can come in conflict with computational load advantage actually. Every grid point you are doing less computation, but you have to take several grid points because delta t you will be required to select much lesser actually. So that way it is not that advantage actually. But in general it has computational load. It has also like closed form further algebra is possible in closed form like that actually. The another thing that comes to method is Runge-Kutta method, and then Runge-Kutta methods are of various orders. It can talk about second order Runge-Kutta, third order, fourth order like that actually, which is very popular in systems theory, and most of the differential equation solution numerical solution is fourth order actually. And fourth order solution, essentially the concept is like that, derivation I will not give here. We will talk about some function, okay, that f of t n x n is something like this, let us say, and you have some value like that here. Then it attempts to find some approximate slopes here actually. Point number 1 you already have the slope. It predicts what is the slope at point number 2, point number 3, point number 4, and then tries to kind of fit a polynomial in between that actually. Okay. And then evaluates that. Using this polynomial you will be able to kind of march ahead with the solution here with much more accuracy actually. That is the philosophy. Okay, more algebra part and all you can see a numerical methods book actually. Okay. So ultimately what it tells me is I start with this series of computation. I start with k1 rather, which is simply the function evaluation there, whatever function I have. Then using that function value, whatever function value k1, okay, I will be able to calculate a k2 actually. Okay. And then using this k2 I will calculate this k3, using this k3 I will calculate this k4. And using all these k1 to k4, I will just try to kind of get delta t over 6 and then average out all these actually, k1 plus 2 k2 plus 2 k3 plus k4. So 1 plus 2 plus 2 plus 1, that is 6, divided by 6 sort of thing. So this entire formula, the final formula xi plus 1 is given something like this actually. Okay. And essentially it turns out that Runge-Kutta, fourth order Runge-Kutta algorithm has error delta t to the power 5th, okay. That means it is highly accurate actually compared to that. Remember Euler integration had accuracy of the order of delta t square only. Now that square has gone to power 5th actually, okay. So that is why it is much more accurate actually, okay. So and the second comment is this method essentially uses a fourth order power series approximation, Remember that Euler integration uses only linear term. Now this one uses up to 4th order power series approximation in Taylor series to come up with this algorithm. Again, details of that is not here. You can see some numerical methods book actually. Okay. And this particular algorithm is popularly called as RK4 method, 4th order Runge-Kutta method actually. This is very popular in MATLAB. You can use all this, and probably for Euler you don't need an integration formula. I mean, it is just that formula is so simple that you don't need any integration formula. I mean, any routine for that actually primarily. Okay, because this integration formula you can simply write it long end actually. Yeah, once you evaluate this f of x actually, then it is easy to just plug in there. So they don't need a formula per se, but this algorithm requires a little bit of evaluation of computation. I mean, little bit of sequential computation. So the formula is available there, and in MATLAB you can see some of these. This is something called ODE23. That's the function. Okay. And there is another function which is called ODE45. Okay. And ODE23 it is this what is called as RK2 method. Okay, second order Runge-Kutta method, and this will give you RK4 method. Okay, so 4th order Runge-Kutta method actually. Okay, essentially both are similar functions, but with difference that these are there. And by default, whatever is there in MATLAB, it is what is called as adaptable step size. Okay. That means your delta t that you are using does not necessarily remain constant actually, and it is adapted provided suppose you have a function something like this. Okay, and then you have this is the for here the slopes are not changing fast, here the slopes are not rather changing that fast, but here in this segment it is changing rapidly actually. Okay, so it will try to see this where the slope changes happen in a rapid way, and if the slope change of slope is high, then correspondingly it will adjust your delta t small actually. Remember, this is your delta t. Okay, this delta t is small here, this delta t can be large here. Okay. So this adaptation of delta t happens in an implicit way inside the algorithm in RK4 and this ODE45 routines and all that. But most of our type of applications we don't we are okay with the constant step size. So you can probably write this function ourselves also many times, and then see what is the delta t that you can select actually. And constant step size is also very good for implementation concern. You don't have to monitor what is the delta t. Every control cycle update, guidance cycle update like that is fixed by some number. So you start using that particular number in a constant step size way actually. So that is some of these numerical methods are useful here. So with that I will probably stop here, this particular class. And you will see that root finding both in linear equation, nonlinear equation, numerical derivative and integration, as well as numerical integration of differential equation. That is all we discussed in this class. These are all useful in our control theory, and many of these practical usage implementation will come from your experience as you work with different problems actually. I hope this will be useful in your further exercise. Thank you.